Okay, so I emailed out the quiz yesterday, right? Everybody got it? Okay. And make sure you read that little preamble thing there, right? Right? It's the only time I ever use the word preamble. You know, it's just the Constitution and quizzes, or Bill of Rights, or wherever it was. I don't know. Something like that. Okay, so we're talking about, we're starting at the beginning of acoustics. You know, it's a simple harmonic oscillator, mass on a spring. And we have no drive and no dissipation, right? It's the free, we call it free oscillations. That's really where it all begins, as you will become aware eventually. And leads to a very simple differential equation. Here it is, as we've seen. And then we launched off into all this use of complex numbers, right? So now finally we can see, we can illustrate the complex method, okay? It doesn't work, this is so simple, it's easier not to use the complex method here. But when we put in damping, which we're going to do next, you want to use the complex method. You do, okay? So here's our basic differential equation. It's a differential equation of simple harmonic motion. It's Newton's second law with Hooke's law in there. And the method now is to make this complex. So we just, in this case, we just assume we go to a complex x, okay, and we're going to solve it and then take the real part to get the actual x. And when you see an equation like this, the natural thing to try is a general exponential. Because an exponential, when you differentiate it, you get the exponential back, right? You got to use the chain rule, of course, but you can differentiate an exponential anytime you want to. You're always going to get that function back. That's a property of exponentials, right? So it's natural to try that. And, well, we could do the same thing here, but you need to go complex because the coefficient of the time here is in general is going to be complex. So when you do that, you can do this in your head. You get two derivatives by we get this back, right? And we're going to bring down 2 powers of gamma here, in general, this complex number. And now for this to be a solution, which means, you know, to have motion, non-zero amplitude, this factor right here has to be 0. So and we want to be complete here. We want to get the general solution. We have to write down all the solutions. There are 2 solutions to this equation for gamma, right? Gamma is plus or minus I times omega naught. Because when you square it, the plus or minus goes away. And you need to respect this. You might think, oh, here's the solution. But to be general, you've got to recognize that there are 2 solutions here. So now we take this, put it back into our complex solution, and we can work with it a little bit, and then we'll take the real part. So here it is, substituting this back into our solution. We get this. Now remember, these are in general, we get 2 solutions, right? Each solution has its own arbitrary complex amplitude, because we're doing everything complex now. So we would write the general solution like this. And now we can go in, before we take the real part, it's easier to remember that we can express a complex amplitude as a real amplitude times e to the I phase. So that's what I've done going from here to here, and from here to here. And now if we take the real part, right, this is real, these amplitudes now are real. And the real part of this is just going to be the cosine of omega t plus phi1, and similarly here. So we take the real part and we get this. The cosine of negative an angle is the cosine of the angle, right? The cosine is an even function. Cosine of, you know, I can multiply in here by -1. I'm not going to change the cosine. So that's convenient. We can write it like this. And then you need to recognize that this is the sum of 2 sinusoids of the same frequency. That's going to yield you a sinusoid of the same frequency. You can get that from a trigonometric identity. It's also physically very plausible, I think. So our solution here has to be of this form. it's going to have to be some kind of amplitude which is related to these amplitudes and the phases too. And it's going to have to be omega naught t, because these are both going at that frequency, omega naught. And there's going to be some phase angle here. Now if you really want to, you can determine this amplitude and this phase in terms of these amplitudes and these phases, but people seldom do it, okay, unless you are doing some kind of exercise. It's really no point to it. This is, we recognize this as one form of the general solution, right? So you'll notice this is not real clean here. So it's an unusual situation. The complex method is trouble for this simple differential equation. It's when it gets more complicated that it beats out the other method. It's a weird situation. So what I'm telling you to do is you can forget this. I'm telling you to forget this. In a sense, that's what I'm telling you to do. Nobody does this, okay? Except this is a learning environment, right? We're learning. And you know, now that I think about it, maybe I shouldn't do it. Maybe I should just put a big X here. We should just go to the next step. Put in damping. That's going to be the next step. And there it's useful to use complex numbers. And when you put in drive in addition to the damping, then it's even more convenient to use complex numbers. Okay, any questions? But it is important to see that it does work and to illustrate the method. But it's really clumsy here. It's clumsy. You know, it's like you're trying to kill an ant and you have a baseball bat or something like that.
Is there a difference between your the complex X with a bar above and below?
I'm sorry?
Like X complex is with a bar below? In the
yes, yes.
And in the middle of the page.
Oh, I don't know what happened there. Okay, that's a mistake, okay?
Average X.
Yeah, this is the average X. Boy, I didn't even notice that. So when this usually happens, what I sometimes say is somebody snuck into my office and changed the node. It's a joke. Okay, I won't use that joke anymore. Okay, thank you. I will correct that. I don't know how that happened. Okay, any other questions or comments? All right, so now let's get to it. We want to be realistic here, right? So all oscillators, except quantum mechanical cases, are going to have some kind of damping. And even quantum mechanical oscillators, you think something would oscillate forever, forget I said it, let's just not go there. In typical, realistic, everyday oscillations, you know there's going to be some kind of damping. You're going to be losing mechanical energy. Another word we use is dissipation. There's some kind of dissipation there. So the simplest form, how do we mathematically model that? Well, the simplest form, it's not always a good model, but the simplest form is that there's a resistive force, this stands for the resistive force, is proportional to the velocity. So if the oscillator is just sitting there, there's no damping on it. You know, the damping is velocity dependent. Well, that's good, okay? And it's in the opposite direction of the velocity. So the object's moving this way, there's going to be a force, impeding force, a resistive force this way. When it moves this way, it's that way. That's why we have the minus sign here. And then we have a coefficient that will characterize the strength of the damping. So this is a good model often in transducers, okay, which is a huge field of, you know, it's one field of acoustics, and well, in other disciplines too, but electroacoustic transduction, you know, like microphones and loudspeakers and sonar devices, that's a whole area of research, and among many other areas in acoustics. So this often works for transducers, which is fortunate. The reason it's fortunate is you see that this is linear in the velocity, and that means we're going to be able to solve it when we come up with our differential equation. Often, if you throw something, you know, if I threw this, I'm not going to do it because the chalk will break. If I threw this through the air, do you think the damping? Some of you must know some fluid dynamics. Do you think the damping is this going to model the damping? Well, some people who took the mechanics course, 2000 level mechanics course, we talked about this. No, in fact, one of my favorite examples is that. So I'm moving my finger through air. There is an impeding, a drag force. Often in this case we call it a drag force. Do you think it's modeled by that? No, and the reason is turbulence. When I'm going like this, if we put some smoke in here, we would see that there are these eddies back here. That's turbulence. There's turbulent flow, and it's not simple. Turbulence is never simple. If I move my finger extremely slowly, it will eventually, if I move it slowly enough, this will be the appropriate model, but it has to be really slow. It has to, such the flow is laminar. That means nice and smooth flow. So this is a little bit of a warning. I want to make sure you understand that this is just a model. It can be derived in some cases. When an object is moving through a fluid, if the Reynolds number, this dimensionless number that characterizes the flow, some of you have probably heard of it, if the Reynolds number is much less than 1, then the flow will be nice and smooth, and you will have a damping force proportional to the velocity. But in typical cases, it's got to be moving really slowly. But there are many other cases where damping comes about, right? And in those cases, sometimes this works, sometimes this doesn't. What about friction? You know, this is dangerous. I shouldn't be doing this. This comes to rest, right? There's an impeding force. What's the frictional force like here? Anybody?
UN.
Yeah, well, right. Coefficient of friction times the normal force. It's a constant, so they tell you in introductory physics, right? In elementary physics, there's a constant force here. It's not this. Now, in reality, that constant force is just a rough approximation. There are situations, it's really actually, it has some velocity dependence. So there are different, different resistive forces have different models. And this one works, sometimes it doesn't. And it will work, we'll be able to get a lot of mileage out of it in acoustics, as you'll see, fortunately, because it's linear, as we'll see. So here's we draw a circuit diagram. Everyone's familiar with electrical circuit diagrams, right? This is a mechanical circuit diagram. And the two are not independent of each other. And one of the things we're going to do in this course is get in your heads the idea of an equivalent electrical circuit. We have a mechanical system, and there's going to be an electrical circuit that's essentially the same as this. And by that I mean if you can solve the electric circuit, which you usually can more easily than mechanical circuits, you know the solution here. So all acousticians know this, and many people use equivalent electrical circuits. They're indispensable in transduction. So we're going to get that in your head, so you get used to this. Here's a spring, here's a mass. What's that? Yeah, well, yeah, it's right. We call it a dash pot, okay? And what it does, it actually is displaying for you what it does. Does everyone get the idea here? There's a little gap here. This is like a disc. This has, rotational symmetry. So you want to think of this as a disc. When there's relative motion here, this is fixed, right? When this moves, the air or whatever the fluid is has to go through that little gap, and that introduces damping. These things actually exist. We have one in the demo room, okay? And they're similar to shock absorbers. Now, to be honest with you, I don't really... What does a shock absorber look like? It has a piston in a cylinder, right? There's going to be some kind of valve. It's the same principle. There's some little kind of valve or something where the air has to go through, and that's where the damping comes about. Does anybody know what oh, wow. That's what happens, things change. So I used to work on cars all the time because I had to, because they'd break down when I was young. And then they stopped breaking down as much, and I got older, and I just don't work on cars anymore. Who wants to work? And they're so complicated, right? Anybody work on cars here?
Suspensions?
Pardon me?
About suspensions, cars?
Well, just in general. Nobody changes their own oil anymore, do they? Somebody does. Nobody changes their own oil anymore.
Cheaper to take it to the place.
I know, but I know, things change. What?
My dad gives me crap. He's like, you don't even, like, that's his, like, you don't even know how to use your, change your own oil. Like, I'll be like, yeah, Dad, I'm getting a master's degree. He's like, yeah, but you can't even change your own oil.
Yeah, yeah. It's welcome to generational gaps. It's very, very common. It's probably been going on for tens of thousands of years. So, but anyway, I bet some distance learning students know, but we're not live right now, right? We're not able to do that. We got problems, technological problems. So we spend our problems doing that rather than changing the oil, because it takes time. Okay, so anyway, it is similar. Let's just leave it at this. It's similar to a shock absorber. Okay. And you need shock absorbers. I don't know if you know this. If your shock absorbers fail, which they don't seem to fail anymore, I used to see it a lot on the road. It's very clear when the shock absorbers have gone bad. But I haven't seen that lately. Maybe they've improved shock absorbers. I don't know. Okay, well, anyway, we bring it back to the lecture here. So here's our net force. We have, of course, the force of the spring, which is dictated by Hooke's law, right? Where X is measured from equilibrium. And then we have our resistive force here. All right, we substitute this into Newton's second, set this equal to the mass times the acceleration, put it into standard differential equation form with descending derivatives where the coefficient's 1. It's pretty standard, right? And this is what we get. So that's our equation of motion for damped, and this is undriven. We call this undriven. We don't think of the damping as a drive. The drive is something that we introduce to keep those oscillations going. The damping is going to, damp them out, right? So let me demonstrate this for you. Here's what I did years ago. I did this once or twice, and I realized it's not right. But you can do this. You can put a piece of cardboard in there, and definitely increases the damping, because the air has to flow around here, right? So I think you can all look at that and realize it's going to increase the damping. So that seemed good, but there's a problem here. If you think a little bit more deeply about this. This does introduce more damping than you have here, substantially more damping, but it does something else. It changes the effective mass here. When you have something like this that introduces damping, it also increases the inertia. It's called the hydrodynamic mass. So anybody took fluid dynamics when you're an undergraduate in here? Do you remember that? May not be in. Yeah. So anyway, So the problem with this demonstration is, we want to take this one step further and ask what's happening. We're going to see that the frequency changes, okay? But in this demonstration, the frequency, it is getting less, but there are two things that are causing it. The fact that we've introduced the damping, we'll see that lowers the frequency. We've also increased the mass, the effective mass here. So I don't do this anymore, okay? Fortunately, though, we have, should we turn on the lights for this?
That's a good idea.
Okay.
I mean, it's not
necessary.
not necessary. But
Okay. There's a spiral spring there. This is German. It costs only $1,200. German stuff is expensive. So the restoring force is by this spiral spring here. So this is a torsional oscillator, because it's an angular oscillator rather than this, but it's essentially the same thing, same idea. There's a Hooke's law here. Now you can see that it's by itself, it's slowly damping out, right? There's some losses in the spring there. When you flex the spring, there's a little bit of losses. There's also some air drag. But the great thing about this, one of the great things about this demonstration is, and I think it's worth the $1,200. Of course, it wasn't my $1,200. Okay. Well, federal taxes. I contributed a little bit, But the great thing about this is, do you see what's down here? It's electromagnet. Okay. This is a conductor passing through a magnetic field, and you get magnetic damping or magnetic braking. When a conductor passes through a magnetic field, eddy currents are generated. Those eddy currents interact with the magnetic field to cause the object to slow down. That's been proposed, incidentally, to get rid of arresting cables on aircraft carriers. by a Berkeley physicist. I heard him talk about it once, and the Navy wasn't interested. I don't know why. You can also launch something electromagnetic. Is that being done? You typically have, yeah, there are rail guns. What about an aircraft on an aircraft carrier? You need to launch it, right? At least you do in the movies. That's all I know what I see in them.
I think the new one, the one that's about to get commissioned, has got, instead of a steam catapult, it's got an electromagnetic.
Yeah, right. So that's more the electromagnetic actually is more complicated. How do you have to arrange that? You got to phase it right, I think. The electromagnetic damping is just universal. And in fact, after the lecture, if you want to come up here, I can turn the current. I can control. Right now, there's no current through there. But when I turn the current on, there's going to be a magnetic field. And let me show you what happens. So before, we had this, right? Very weak damping. I turn on the current. Big effect, right? And you can feel it. You can feel it. So there's nothing going. It's just a conductor moving in a magnetic field. It's really not very fancy at all. And very effective. So let me first of all show you, here's a small amount of current, relatively small. We still get oscillations, and you can see that they're damped. They're a little bit more damped now than they were when I didn't have the current on, remember? Okay. We can also, I'm sort of getting ahead of the story here. Okay, let's hold off on this. Let's wait till we do some more analysis. All right. Oh, can somebody get the light? Sorry. Let's solve, and we're going to use the complex method, okay? So here's we make in this case, it's very easy to make the equation of motion complex. We just, everywhere we see an x, it becomes, which is real, we replace it with a complex x, okay? And again, this begs for an exponential solution. The same idea as before. And now we pick up another term. This is our additional term here. So this is what we had before. We get this additional term here. And now, just like before, this has to be 0. And we want to write down the most general solution. And here we just we use the quadratic solution. This is a quadratic equation in gamma. And the solution to the quadratic equation in real variables is the same as complex, right? In fact, often you're forced into, when you write down a quadratic solution, often you're forced into dealing with complex numbers because you're taking the square root of a negative number. And there's no problem with that in the complex land, right? So here is the solution of the quadratic equation. We set this equal to 0. It's quadratic, and you can see the usual minus b plus or minus the square root of b squared minus 4ac over 2a, everything you've known for a long time. So here's the quadratic solution. We can beat it into a little better shape. We're not going to do much here, but we'll do more in just a moment. Let's put the 2 underneath here, and we get this. And now you can see it's convenient here to define a quantity. It's called the damping parameter. And it's the mechanical resistance divided by, does anybody want to guess why? Young knows. Why this R has a sub M here? The M stands for mechanical. Does anyone want to take a wild guess? Why don't they just call it R? Because we're going to use R for electrical resistance. So they're already setting the stage for equivalent electrical circuits without you knowing it. But I gave it away. Okay, so you may wonder, why do that? Why just drag around that extra subscript? It's because we're going to be looking at equivalent electric circuits, and we want to reserve R for the electrical resistance, which has completely different units than this, okay? It's a different quantity. It's analogous, but it's a different quantity. So we define the damping parameter, and now it looks a lot simpler, right? And now you can see there's 2 basic types of motion here. When beta is less than omega naught, we're going to be taking the square root of a negative number, right? That's going to introduce an I out here. And that's going to give us, as you'll see, that's going to give us oscillatory solutions. So that's called weak damping. Okay, excuse me, underdamping. Weak damping is when beta is significantly less than omega naught. But all we have to do, if we have beta less than omega naught, we're going to get what's called underdamped motion. And you'll see in the solution, that means there's going to be oscillations, but they're going to be dying out. What about when beta is greater than omega naught? What happens then? Now we have our two solutions here. We got to use the plus or minus. But you can see there are no i's anywhere. This becomes just totally real. And if you go back and look up here, we're going to have decaying exponentials. No oscillations. That's overdamped motion, is when you have no oscillations. And then somewhere between these two, something happens. You can see when beta is equal to omega naught, this is equal to 0. That's the crossover case. That's where you're going from as you increase beta, you go from underdamped to overdamped. Right when beta is equal to omega, that's called critical damping. And let me demonstrate that. And critical damping is important in shock absorbers. And I'll show you why. So here we are. Here's our weak damping. So it's a little bit more than just the drag and the loss in the spring there. I've got a little bit of current going through the electromagnet. So that's underdamped motion, okay? And then, see, I think I can go to, that's amazing. There's no contact friction here. This is electromagnetic damping. It's amazing, isn't it? Yeah, but you got to have that cable. You can't do it. You know? I'm talking about the aircraft carrier stuff for you. Yeah, it's just really remarkable. I mean, they probably were worried that it would fail, right? The power would go out or something, and you're in trouble, right? Okay, so this is overdamped motion, and somewhere in between, and it's right about 13 volts on the scale here. Right in here, it comes down, it goes, the critical case, it goes to equilibrium the fastest, and it does not overshoot. If I increase the damping a little bit here, you're going to find that it just takes longer to get there. If I decrease the damping a little bit, it overshoots a little bit. I mean, I can do that. Let me go down to 12 volts. See that? That's not quite, it's overshooting, so it's not quite critical. So what you want with shock absorbers is you want to bring the suspension back to equilibrium as quick as possible. So you want them to be critically damped. And when they're not, as they start to get old, at least in the past, a car would go over a bump and the car would just oscillate. It would be underdamped. And I used to see that a lot, but I haven't seen it in many years. So I don't know what's going on. I don't know. All right. Okay, we're going to do one more demo.
Professor, were they built to be underdamped like that, or was that just a product of like later?
Yeah, that shocks fail. You know, there's some way it's similar to the dash pod, right? And things have warped, or I don't know. They're failing. They're not damping as much as they should. And so you get underdamped motion, and it can be really noticeable. But it's typical. I have to say, when I saw it in the past, it was usually very old cars. I mean, not Model T Ford, but they were old. But I haven't seen it in a long time. Okay, so what we're going to be, for the acoustic sequence, I think it's all underdamped. In fact, it's typically weakly damped, as you will see. But everyone knows about it. You want to always keep this in mind, because when you do research, you can encounter things. So it's always good to keep this in mind. So let's focus on the underdamped here. I don't know, highly, weakly. Ignore this, okay? What I'm saying there. That's the typical case. Oh yeah, I have typical here. Yeah. Okay, I guess that makes sense. Yeah. So typically this is what we're going to have. We don't need to make any approximations yet. Let's just stick with the underdamped. Let's not make any approximations till we have to. So we're just assuming now that beta is less than omega naught. We're not saying that it's much less, okay? So now, because we have a negative number here, we factor out an I. So you can see what we've done going from here, this radical here to here. We introduced a minus sign two minus signs. The square root of one of them is going to be I. And now I've made this into a positive quantity because we're going to assume now that beta is less than omega naught. So here's our gamma. We can write it like this. We're going to call this omega sub d for the damped frequency. And you know what's going to happen here because this has no I and this has the I. This is going to be the oscillation frequency. And as I mentioned before, in the presence of damping, an oscillator has less frequency. Although it's usually it's less by a very small amount. I'm going to try to impress that upon you here. Let me tell you right straight away that typical acoustical type situations, beta is small compared to omega naught. And because these are squared, it's typically a very small effect. And I'm going to demonstrate that for you. So let me just get this in your heads right now. Almost all acousticians, when they deal with this, they just set omega d equal to omega naught. Very common. But everybody knows that you have to be careful. You might be in a situation where it's not weak. The damping is stronger. So here's our general solution. Now that we found, we're still complex here. We found our gamma, our complex gamma. We substitute it into here. And we have two solutions. Remember the plus or minus, do the quadratic equation. So we've got, that gives rise to the plus or minus here on the omega d. All right, we can factor out an e to the minus beta t, this exponential decay here due to the damping. We can factor it out. And I've also gotten rid of the complex amplitudes, and now we can take the real part. And as we've said several times before, we're going to have these two sinusoids here, but they're both going at the same frequency, omega d. So the solution's going to be this, just like we were talking about in the first part of the lecture. So that's the general solution. You'll notice that it has, how do I know it's the general solution? What's the rule? We have two independent undetermined constants, A and phi. And we have a second order differential equation. So as far as I know, as long as they're independent, they don't depend upon each other, you can set them independently. That means you can meet any initial conditions. That means you got the general solution. Okay, what it looks like is without the damping, this is not there, and this omega d becomes omega naught, and it's just a sinusoid. That's with no damping. When the damping is introduced, we have this exponential envelope here. I've sketched it as this dashed line here, and also down here. Causes the typical way of thinking is we have this amplitude. Here's the overall amplitude, and it's decreasing in time. That's the way often people look at it. So there's this envelope here. So the amplitude is going down. And the frequency is less than the natural frequency, or the undamped frequency, omega naught, the square root of k over n. Which is reasonable. I think you'd expect that the damping is going to slope reduce the frequency. However, you'll be surprised, we call beta the damping parameter. So here's something, I don't know if I've ever done this before. I tested it, of course. You always want to test demonstrations, or you can make a complete fool out of yourself. If you ever get in that situation, keep that in mind. I know, because I've done that before. So here we have, we're going to focus on this omega d here. Here's the natural frequency. When I have no current, the best I can do here is just have no current. And I get these oscillations. And let's time 10 oscillations. Okay, we've done this kind of thing before. I'm going to let it go. 1, 2. $17.57. Is that right? Okay, now, that's approximately, it's not exactly equal to omega naught because we got some damping there, but it's, it's going to be pretty close. Now I'm going to dial up Now I'm going to do the 2 volts. Remember, that's the sort of the... Okay, so 2 volts, here's what it looks like. And you can see it's definitely... Now I think we can just eke out 10 oscillations here. We have to do that to get more accuracy here. So let me reset this. Okay. Let me get this going. 1, 2, 4, 5, 6, 9. God, that's what happened this morning. This is amazing. This is 1 part in like 2,000. Okay? This is see, that's the way we think about experimentally, right? This is, I basically have, 2,000 here approximately, and we're accurate to 1 part in 2,000. So that's, that's a 0.5%. And the same thing happened this morning, and I can't. That's really it's a coincidence, I think. Or maybe there's something else going on around here. I don't want to. Okay, so this is a good demo. I don't know if I've actually done this before. So you could see, when you see this, it's significantly more damped when I have the 2 volts on there, right? So what's happening here is this. Beta does not have to be all that small because of the squares there. Because this is squared, beta could be 10% of omega naught, which doesn't sound like a small beta. But when you square it, it's down to a 1% effect. When you take the square root, it's a 0.5% because of the approximation we make with the square roots. If you don't know about that, don't worry about it. We'll do it later. Taylor expansion or binomial expansion. So because of these squares here, very often you can just replace omega d with omega naught, and you just saw it right there. Okay? But in general, if beta gets bigger, you'll eventually see that frequency decreasing. Some words here. Again, beta is the damping parameter. KFCS also call it the temporal absorption coefficient. They're setting the stage for next quarter. It's kind of early to talk about next quarter, right? We're in our 2nd week of the 1st quarter here. There's a spatial absorption coefficient. Sound can attenuate, and that's a big topic in the next course. Being able to calculate how sound attenuates is useful. It's useful to know that, and you can imagine applications. So it's also called the temporal coefficient. And you'll notice here that the characteristic time for the decay here is a time equal to 1 over beta, because then you're down by a factor of e, which is roughly a factor of 3, right? E is 2.7 or something, roughly. So the rough decay time here is 1 over beta. It's when the amplitude has decayed to 1 over e times its initial amplitude, and that's often called the relaxation time. This oscillator, its final state, it's relaxing to its final state, which is it's not moving at all. Damping causes that. And there's a characteristic time for it to relax to no motion, and it's 1 over beta. You can see from here, it's the 1 over e time is 1 over beta. So it's good to know this, especially when you're doing research. You need to be aware. I just hit it yesterday with one of my thesis students. It's important to know the characteristic time, as you'll see. We'll show examples of that. Sometimes it's very quick, you don't have to worry about it, or sometimes it takes a long time. And if you're taking data, you want this to be quick, right? If you have any kind of, the idea of a relaxation time is very general. It's usually a time you have to wait before you take some data. And often people will, it's called a time constant often in that case. And often people will wait 5 time constants to get an accurate value. So it's just good to know this characteristic time for it to decay here. And that's what we call the relaxation time. Okay. All right. So going complex seems to never end, right? One of the things we're going to be doing in this sequence, and I know it's going to come up next quarter, I don't know if it's, to be honest with you, I don't know if it's going to come up with this quarter, is we can generalize, we let our variable x become complex. You can let parameters become complex, and that can be useful. And I know it's going to be useful next quarter because I've taught that course many more times than I have this course. But we just want to state it now and get it in your heads. We have two quantities here. We have this damped frequency and we have the damping parameter. We can combine them into one complex quantity here. The real part is the damped frequency. The imaginary part is the damping parameter. And you can see that if you take this and substitute it into here and just stare at it, you'll see that you get this, right? Because I times I is -1. So you just take this, and if you can't see it, you can write it out. Just take this expression, subs it in there, and you get there. So this is, it sometimes happens, things are actually simplified by trying to reduce the parameters. We've really brought these under the umbrella of one quantity here, one complex quantity, and it can be useful. Okay, any questions? That's amazing. I really want to do it again. But to do this twice in a row and have no fluctuations down to this tiny, one part out of 2,000 here, that's very unusual. So no questions? Okay, so what's next? So oscillators will die down, and often we don't want them to die down, right? Like a loudspeaker or something like that. We want to keep them going. So there are different ways that you can maintain. There are different ways that you can keep oscillations going. I don't want to use the word maintain. How do we keep oscillations going? Well, it's interesting. There are actually 3 ways that I know of. 3 very different ways. We're going to study the simplest. Okay, it's where you exert an oscillatory force on the mass here. Just exert an oscillatory force on the mass somehow. There's also so this pendulum right here. You can imagine me exerting a force back and forth on this, right? An equivalent way to do it is to drive the support this way. Now that's not real obvious, but if you go into a frame of reference where the pivot is at rest and you're moving back and forth, what do you feel? What if you're in an elevator and it's going like this? Elevators usually don't do that. I wish they did because it's great physics. What do you feel in an elevator doing this? You feel alternately heavier and lighter, right? So it's as if the gravitational force is modulated, right? It's not a constant. When you're in an elevator, it's just not moving. You just feel this constant gravitational force. We call it's your weight, right? If the elevator is going up down, in your frame of reference, you actually feel g, the acceleration due to gravity, is actually being modulated. And that can be done. This is like we call this a direct drive sometimes to distinguish between different types of drive. The parametric drive, because we're modulating the parameter g, it's called a parametric drive, you get by oscillating up and down. And look at this. And I'm not even trying to do this, okay? You see how I'm feeding energy in there? That's called parametric excitation. Okay, and if you want to know about that, here it comes. Okay. So this is the nonlinear course that has no tests, right? That we want to offer next spring, right? And we didn't offer it last spring, and now we went over this. So it's great to do a tutorial class though. I haven't done it in many years. To sit around a table and discuss something you've studied and do some problems, talk about it, it's great. It comes from Oxford, hundreds of years ago, Oxford University. And it's just not feasible. You only can do it with a few similar students. But that's what we're doing for the directed study, and it's just great. I'd forgotten how good it was. But anyway, the distance learning students, this is not in the sequence, but if you make enough noise and you want it to be, nonlinear oscillations and waves, maybe we can get it in there. It hasn't happened so far, but that doesn't mean it's not going to happen, right? So anyway, hopefully next spring, right? So there's a third way. excite oscillations. It is the most common and the most difficult to calculate. Anybody know what it is? Every kid knows. Oh, here's an example. Ooh, I bet that pegged the sound. Gene did it. Sorry. How's that work? How does a... There are many examples in musical instruments. Dragging a bow across a string for a violin. How does this steady motion excite oscillations? How did the original Tacoma Narrows Bridge come down? Does everybody know about the original Tacoma Narrows Bridge? Wow. So the wind coming off Puget Sound drove these oscillations of the bridge, and it broke the bridge. 1940. One of the most studied disasters of all time until 9/11. Do you guys know about the Tacoma Narrows Bridge? Somebody doesn't. Wow. Pardon me?
Excite the natural modes.
But how? How does the wind wasn't pulsing at this frequency. I can guarantee you, well, the wind by itself was not pulsing. Somehow the interaction of the wind with this mode caused energy to be fed in. That's the idea of a maintained oscillator. They're fascinating, they're all over the place, and they're hard to explain. And this is a maintained oscillator. I'm just blowing with I'm just going like steady flow, right? How can I support the oscillations in here? Well, that's a maintained oscillator. That's the third kind. So we have a whole chapter on that, chapter on parametric excitation, chapter on maintained oscillations, and then, of course, the simple stuff. Okay, so let's do it. Let's start it. We're going to start it. Here's our circuit diagram. Now we put this force here. The arrow signifies that that's the positive direction. This is not going to be an oscillatory force. In fact, we're going to choose it to be sinusoidal. Now, how can we get away with that? Because are all forces sinusoidally varying? No, you could have a force going like this, right? A square wave force. Well, there's something called Fourier analysis. I think, have all you guys had some Fourier analysis? Has anybody not had? Okay. So, if you do have that kind of a drive, so the force in time is looking something like this, you can think of it as a superposition of sinusoids of different frequency. That's the whole idea of Fourier analysis. So the point is this: once we've solved for the response of the system with a pure frequency drive, pure sinusoid here, at any frequency, we can superpose the results. This is all linear to achieve this or anything we want to, any periodic force. And even aperiodic, well, we'll see. So that's why we, and another reason, this is going to be much simpler to solve. This is what you want to solve. You don't want to directly go to try to solve something that's non-sinusoidal. And what's more complicated. So we're going to consider the sinusoidal drive, and we're going to go complex. So here's our equation of motion, right here. And I'm sorry, you want to imagine that capital F times cosine omega t is here, okay? When we go complex, we make the x complex. And then what we really want to do here is, remember, we're going to take the real part. The real part of this equation is going to be our actual equation. You really want to set the force equal to e to the I omega t. It allows this, you don't, technically, I never thought about this until last night. I don't think you have to do this, but you make life much easier if you replace the cosine with an e to the I omega t. And of course, the real part of this is what? It's f times the cosine omega t. So here's our complex equation, and again, and once we've solved it, we're gonna take the real part, okay? And you can see that this is all we're ultimately interested in, the real part here, and the real part of this is going to be our actual drive. And this could be a sine of omega t or any phase in between. You would accordingly change it there. Okay, now, this is not a homogeneous equation. There's not a zero here. There's a term that doesn't involve x. It's linear in x except for this term, so it's called inhomogeneous. So do you remember your differential equations? How do you solve this? There are two solutions to get the general solution, right? There is what's called often the homogeneous solution. You set this equal to 0, okay? Solve for this, as we've already done. That's going to give you two independent constants that you can use to meet initial conditions. Then, that's the homogeneous solution, because this is 0. Then we need to find the particular solution. There's going to be a unique solution that satisfies this. And you add those two solutions together. That's the general solution. Now we have a more physical way of looking at it here. This homogeneous equation is going to die out, right? When this is equal to 0, we know this is a damped oscillator. So we usually call it the transient solution, because it dies out. And it dies out at a frequency omega d, remember? The particular solution, we call that the steady state solution. And the idea is this, is that when you're driving an oscillator, when you switch the drive on or you change the drive, there's going to be a transient period where the motion typically looks very complicated. It'll die out in this characteristic time it takes this to die out, and you're just going to be left with the steady state solution. The steady state solution, we're driving at some frequency. The oscillator will be responding at that frequency. Now, how do I know that? Well, I think it's very plausible, but we're going to prove it mathematically tomorrow, that the steady state solution, and this is almost always what we care about in acoustics, is the steady state solution. You've got to weight several of those time constants, or decay time, what do we call it? I've already forgot. Relaxation times, whatever you want to call it. Once you weight several of those values, the transient solution will be gone, and you're going to be in the steady state. And almost always what we're interested in is the steady state motion. But there will be this time in the beginning where you have both the steady state and the transient. And you're going to have, in general, two different frequencies, and the motion can look quite complicated there. But it'll be very simple after the homogeneous dies out, and we just have that. It'll be moving at one frequency. So that's what we're going to solve for tomorrow. Okay, anybody have any quick questions or comments? Okay, start thinking about analyzing the data for the lab, right? And you want to come up with preliminary reports, and then let me see them. The distance learning students should do similar things.
Oh, wow.
We still have to work out how that's going to work. But I've already started to get some questions about it.
What's your expectation for kind of how long the lab report?
Oh, as long as it takes, or as short as it takes.